Physics time, we're talking about today circular motion. So write down your objective. Oh, I already have it written up here, but it is calculate and describe circular motion. So we talked a little bit about the definition of circular motion. Do you remember I asked you, does it have to be moving in a whole circle to be considered circular motion? No. Circular motion is any time that motion is curved. When it has both an x and y component to its motion, it becomes circular, right? And so a projectile motion counts as circular motion. And we generally don't think about it that way because projectile motion is something we study kind of separately, but it is true. So circular motion is motion of an object along curved paths, right? So generally, obviously, we're thinking about it moving how, though? Not always, but generally how. Mm-hmm. In a circle, Whoop, there we go. That's a fairly good circle. The first thing we usually talk about with this is the distinction we make between rotation, you read this in your book, and revolution. And just, whether you read it or not, can you tell me what these things mean and how they're different from one another?
Isn't rotation just like spinning?
Yeah. So generally we can think about that. Like rotation is what we might have in kindergarten called spinning, whereas revolving is moving around something in a circle. The physics definition, let's try to be a little bit more, I don't know if specific's the right word, but let's try to be a little bit more methodical with the way we phrase this. What could we say is the definition? What's true if I rotate this marker, right? Whereas if the marker revolves around my podium, right? How can we tell the difference between those two things in a physics definition?
Rotation stays upon the same axis?
Yeah, rotation, well, let's do it this way. This is going to make it a little bit easier. Rotation and revolution. Rotation is spinning about an... Oh, why does that say that? You may be having performance issues. Well, I don't know, it's gone now. Spinning about an internal axis, and this is moving
external.
Yeah, in circles. Oops, let's at least spell circles, right, if we're talking about circular motion. Moving in circles about an external axis. So the easiest and best example of this is the solar system, right? So if we have let's just make this circle I drew earlier into the sun, and we have Earth here, right? This is not to scale, obviously. Earth is much, much further away than that and much, much smaller. But anyway, this is little Earth. Earth rotates. What do we call that when Earth rotates? What passes as Earth rotates one time? A day, right? This little spinning of it about its own axis is called a day. But Earth, in addition to rotating, Earth also revolves, right? And in one revolution of Earth, right, one rotation of Earth is called a day. One revolution of Earth is called a year. This is one of the most... I think it looks nice from a distance, but I have the word year way up here by circular motion. It's not a very neat board at the moment, but I think it makes sense. You guys get good on that, rotation and revolution? Okay, so another thing we talk about with circular motion is obviously we're always in physics very interested in measuring the properties something has. So how can we measure circular motion? There are two ways.
The amount of times it spins per...
Okay, so we have something called angular velocity is what we normally call it. Your book calls it rotational speed. But those two things, you see how they're the same, right? Mm-hmm. Angular velocity means that we're measuring an angle per unit time, change in theta over time, right? Equals, and do you remember how we abbreviate angular velocity? This is back to your bell word. Yeah, it looks like a W thing. It's the lowercase Greek letter omega. So where omega is, I'm going to write omega here. Omega is angular velocity. Delta theta is what?
Angle.
Yeah, change in angle. That's why we call it angular velocity, change in angle. And of course, t is time. measured in seconds. Do you remember what we normally measure theta in?
It's radians.
It's radians in the SI. Normally in our life we measure it in degrees, but we measure it, and radians, like I said, was kind of an odd unit. We normally don't consider it to be a unit at all. Like you'll end up with an answer here of theta is just per second. Sometimes we call it rotations per second or revolutions per second. Like if we're talking about the rate at which an engine turns over, right? We get something like 1500 RPM, revolutions per minute, right? And that's a measure of angular velocity. If we're talking about my record player at my house moves 33 RPM, right? It goes around the track 33 times in 1 minute, 33 revolutions per minute. In fact, that's what your book uses as the measurement of this is revolutions or rotations, doesn't matter, that's what's nice about R. Revolutions per minute, that's what RPM stands for. And this is how your book measures angular velocity. It's not the way the SI measures it, and I wouldn't say it's the neatest way, but it is the easiest to understand, that's why your book does it. And then we can also measure what we call the tangential velocity, or the linear velocity. These two things are synonymous. Tangential velocity or linear velocity. And the reason we call it tangential velocity is because, do you know a tangent line to a circle, what that means? Have you ever heard of this? Tangent line. I mean, you know that we use tangent in like trigonometry, but if we have a circle here, a line tangent to this circle touches it at exactly one point. I kind of made it a little bit flatter than that. But this is called a tangent line. Have you ever heard of someone going off on a tangent? You hear about that? And you say, oh, I was trying to talk to my mom, but she went off on a tangent. What does that mean? Have you ever heard that? Okay, well, sometimes people say it, and it means that they got off topic, right? I go off on a lot of tangents, and that means that we're kind of thinking about the conversation as this little circle, right? Going around a little circle, and then they go off some other direction, tangent line. Tangent line is also what happens if I get my racquetball stocking of science out here. Oh man, it's been a while since I used this berry. If I get the racquetball stocking of science out, right, it's moving in a circle, and if I let it go, how's it going to move? In a tangent line, right? In a straight line. If there were no gravity, it would move in a straight line forever, right? Because of this is very important. Why does it do that? Because of its... Yeah, that's how it moves, is along the tangent line, but because it's still moving because of its... Nope, there's no more force on it. What causes it to keep moving forever in a straight line? Newton's first law, which is? Yeah, and we call that, in one word, the object's what keeps it moving forever? Inertia, you got it. Yeah, inertia. So when something's moving in a circle, is this a normal way for a thing to behave? Do things just move in circles on their own? No, because there must be what? What's changing about this? Remember we talked about this at the beginning of the year. Is its velocity changing as it goes around? I mean, okay, is its speed changing as it goes around? That's what you already answered. No, its speed is not changing. It's going the same speed, we'll say. But is its velocity changing? Yeah, because its direction is always changing, right? So if its direction is always changing, is it accelerating? Right, it is accelerating. So if it's accelerating, what must be acting on it? All acceleration is caused by a force. So circular motion only occurs when a force is acting on it. Let's write that down. Circular motion only occurs when a force is acting on an object. Because if it wasn't for a force acting on the object, that you saw, when I stopped putting a force on that pantyhose ball of science, what happened? It went in a tangent line off because of its inertia. So the circular motion only continues as long as the force is applied. And when it stops being applied, it flies off on a tangent line because of its due to inertia. Does the Earth have inertia as it moves about the sun? Speaking of our old drawing. Yeah. It just moves in a circle forever. Is there a force acting on it? Yeah. What's the force pulling the Earth towards the sun? Gravity. So in this case, the force is provided, F is provided by G, right? The force of gravity keeps it in a circle. If the sun were to vanish, what would happen to planet Earth? Keep going in a circle forever? It would fly off in a tangent line forever. And this is what happens in circular motion. The force is always acting in what direction in circular motion? Towards the
axis.
Yeah, well, I'll say towards the center. You're right, but I'm going to say towards the center because it'll be easier. So let's write that down. In circular motion, a force must always be acting towards the center. In circular motion, a force must be always acting towards the center. What provides the force can change, right? Or it varies from thing to thing. In circular motion, a force must always be acting toward the center. And we call this, do you have a vocab word for this? Do you know it? What force in general? The force can be many different shapes. Yeah. Centripetal force. And this word comes from the Latin centra, meaning center, that's easy, and pedal, meaning seeking. You understand how that's helpful? Center seeking. The force is going towards the center, seeking the center, right? That's not enough though, right? If we have two objects and they're being pulled to each other, they just go straight to each other, right? So there must be something else happening to make it be in a circle. And what is that other thing? We already said it several times. The object's what? This object's, yeah, it has some tangential velocity because of its inertia, right? Its inertia carries it along this tangent line. So every second that goes by, it has this velocity because of its inertia, right? And it has this force acting on it, acceleration in this direction because of the centripetal force. So the resultant of these two things is going to be that it moves how? Instead of moving straight towards the center, like the force would have it move, instead of moving straight out, like inertia would have it move, how does it end up moving? Well, eventually, but at this point, what's going to be the resultant of these two forces? Sorry, let me get this. They're equal. What's going to be the resultant of these two? If we have one force acting on it going left and one going up and they're the same magnitude, what's the resultant of these two? Yeah, at a 45-degree angle this way. So this is the resultant, right? So then it'll move, instead of moving up in this diagram, instead of moving left, it'll move diagonal. So now it'll be here, right? And now the force is acting still towards the center, but now its inertia would have it go this way. So now it's going to move how? There we go. The result is that. So now it'll be here, and you see over time, let's be here next, and then here, and over time, it forms a circle. So my pantyhose ball of science, right? It's a combination of inertia and the centripetal force that makes it go in a circle, right? If I release the centripetal force, it goes off in a tangent line forever. What was providing the centripetal force in the pantyhose ball? What kind of force was that? Was it gravity? When I threw it in the lab, so it's gone now. But what force was providing the centripetal force in that case? The force of what on what? My hand on the pantyhose, right? It's what we call the tensile force, right? It's the tension between the pantyhose and my hand that causes that force. With the sun and the earth, that force was provided by still a centripetal force, but it was provided by what in that case? Gravity. So the centripetal force can be any variety of force, but if it's acting toward the center, we still call it a centripetal force. Okay? So we had rotational speed, which this thing will have, in a certain number of rotations per minute or revolutions per minute. Maybe we'll say 1 rotation per minute. And now we're going to discuss its linear speed as well. And so we described what linear speed is, or what a tangent line is, right? A tangent line is the line that off a straight path from the edge of the circle. But now we're going to talk about its tangential speed. So tangential speed and rotational speed are related by this equation. Sorry, let me turn the page. V equals omega r. This is a really, really simple equation too. Can you guess what? Oh, this should have a line over it. What's V, probably?
Velocity.
Yep, V is We're going to specify in this case linear velocity, or we can call it another thing. We just said it. Tangential. Say it.
Tangential.
You say it too, Haley.
Tangential.
Yep. V is linear velocity or tangential velocity. These two things have the same definition. They mean the same thing. We just use them. Why do we have to say this instead of just velocity now, though?
Because you're specifying what type of...
Right, because we also have an angular velocity that we need to be careful of. So V is tangential velocity. And just so you know, the V equals d over t, for instance, that we did all year, that was linear velocity, right? We just didn't call it that because we only were dealing with one kind at the time. So omega is angular velocity. And how do we measure that? What units?
Wasn't it,
Radians.
yeah, radians divided by seconds?
Yeah. And we're just going to put 1 over things. Because like I said, radians is not really a... Like that unit, for some reason, it counts... It's like a Hemi unit. Like we don't really use it in algebra when we work with units. So we're going to put 1 over seconds. And then R is... Can you guess?
Rotation.
No. Good guess, though.
Revolution.
No. Also a good guess. Radius. The radius of the circle. And how do we measure... What kind of units do we use to measure the radius of a circle? Yes, centimeters, length units, right? And in the SI, the length unit we use most often is meters. So if we have angular velocity in 1 over seconds and radius measured in meters, what's our velocity going to be measured in? Meters per second, just like we always measure velocity, right? So this is a fairly simple equation. Tangential speed is just angular velocity times radius. So I love this little picture on page 124. I'm going to try to reproduce it on the board. We have a record player. You guys like music? Have you ever heard of music? What kind of music do you listen to lately?
Oh, I actually have a record player.
Oh, really? What is the record currently on your record player?
Queen.
Queen. Okay, which one?
Bohemian Rhapsody.
Okay, sure. Like the music soundtrack, like the movie soundtrack, or?
No, like that.
Okay, good. And we'll put Bohemian Rhapsody. Is that the name of the album? It isn't, is it? We'll put that on there though because that's... What is it? One of my favorite Queen albums, this is not the point of this class, but one of my favorite Queen albums is called Night at the Opera. You should look into it because you know it. That's a really good one. 39 is my favorite Queen song. Anyway, it's kind of related. 39 is related to physics. YouTube. 39 is related to physics, so I'm doing my job. Okay, so we have a Queen album here on the record player, right? We know that record players, or at least modern record players, move 33 RPM. Okay? We're going to have two. Your book uses ladybugs. I'm going to use ladybug as well, but it's going to be like red dots here. There we go. I know that the diameter of a record like this is about 12 inches, right? We don't use that kind of thing in physics. That's about 20 centimeters. It comes out to be about 20 centimeters. So we're going to say the diameter of this is 20 centimeters, okay? 0.20, I should erase my drawing above, 0.20 meters. So we have 33 RPM, 0.20 meters. What I want to know is we're going to pretend this little ladybug is on the very, very edge. What is this ladybug's linear velocity? Okay, so step 1, which is?
Isn't the furthest one go faster?
You mean the nearer one, or the further one? Or do you say furthest? Yeah, the further one will go faster by linear velocity. We're going to find out why in a second here. So, first of all, let's back up one step. Which one of them has the larger angular velocity? Be very careful.
Closer one.
Try again.
Further one.
Try again.
Both.
Both. Yeah, neither one has the greater angular velocity, because what is angular velocity? How do we measure angular velocity? Which of these things is the angular velocity?
30.
Yeah, 33 rotations per minute. Is this one moving 33 rotations per minute? Is this one? Is the middle? Yeah, all of it's moving 33 rotations per minute, okay? So they all have the same angular velocity. Write that down. They all have the same, everything on this has the same angular velocity. But you know from being on the merry-go-round, and you know from looking at your record player, what thing here, which of my points is going to move faster, be moving faster in linear velocity?
The one close to the edge.
the one closer to the edge is going to be moving faster, right? The one furthest from the center will move the fastest as far as linear velocity. So we write our equation, v equals omega r. What are we trying to find from this equation right now? We're trying to find linear velocity, so we don't need to manipulate. What's my omega?
33 RPM.
33 RPM. Oops, that's not the word. That's not the number 3. 33 RPM times, what's the radius for let's do the outer one first.
0.1.
Yep, 0.10 meter. So this is my velocity. I will say this is 1, this one's 2. So my V1, my linear velocity 1, equals 33 times 0.1, so 3.3. What's my unit going to be?
Meter per second.
Try again.
Oh.
Yeah, this is right. Meters per, not second, because I had RPM. So meters per,
Meters per.
what's the M in RPM stand for? Something per minute.
Oh yeah.
So this is going to be meters per minute. So this thing is going to be 3.3 meters per minute. V2 will be, once again, V equals omega r. V equals still 33 RPM, but now we're going to say he's half the distance from the center to the edge.
So it's 0.05.
Yep, 0.05 meters. This is going to be roughly 1.65, something like that. I'm not terribly, yeah, that's right, isn't it? Yeah, that's right, 1.65 meters per minute. So this one has half the linear velocity of the other one. Okay, we talked about centripetal force. You should be aware that there's this thing called, that people talk about sometimes when they're wrong, called centrifugal force. So we know that centripetal force is the force that acts towards the center of a circle, making the shape of the path circular, right? So far so good. There's this other idea of centrifugal force. And this is what we call a fictitious force. Because it doesn't really exist, at least in the frame of reference outside the circle, it doesn't exist. Depending on our frame of reference, it does exist to people that are acting inside of it. It's kind of a wiggly situation. But anyway, we consider this a fictitious force, because what direction is the force actually acting in the circle? Yeah, well, what's the direction the force is acting, though?
Oh,
Towards the center. Always acting towards the center. But what does it feel like when you're on a merry-go-round? What does it feel like to this ladybug? Yeah, it feels like you're getting pulled out because of, let's just put that, feels like getting pushed out. Let's see if you can get it due to one word. Inertia, yeah. Because at every given second, this ladybug, if the record player were to stop, the ladybug would fly off in a tangent line. And so it's the inertia of the ladybug that makes it feel like, I'm flying off, right? When you're on the merry-go-round and you're getting pushed really fast, what makes you feel like you're going to fly off is not some centrifugal force. That doesn't exist, right? It's your inertia. Because if it were to stop, you would fly off, right? Your book has a little discussion that you should read about how gravity can be simulated with all this, which is pretty interesting. Basically, the centripetal force acting inward and your inertia pushing you out can make it seem to someone like this ladybug, if there's a solid thing here, can simulate gravity. And the ladybug could walk around on side of that. So you read about that. If you're watching this on YouTube, you can look it up on Wikipedia or whatever, but you should also, Morgan, you're going to watch this, you should watch the rest of that Mechanical Universe too. Mechanical Universe episode, Circle episode. Bye! Okay.